talk today will be based on my university work, but before I delve into it, I will talk a little bit about what we are doing at Microsoft because there was some interest yesterday. So my team is developing a platform which processes large data. And we are doing that using a specific component which makes the process very efficient. The component is implemented in Rust. We decompose the data so that we can recombine it and we can run queries. The queries are usually in KQL. And we generate standard Power BI dashboards and display for the customers their usage patterns. We are not concerned with security. I heard that this was a topic that was brought up quite frequently yesterday. We abstract from it. But there was another topic as well. Do we allow customers to use their own firmware? And no, we don't allow that. This is absolutely out of the question. We do not foresee moving into that direction anytime soon. From April, I'm moving to work on the Copilot. The Copilot is the effort of Microsoft to make generative AI usable and to give reproducible answers to queries. This effort, from my research scientist perspective, is doomed, but I haven't said that. Okay, so I will talk about integrity today. Integrity is based on the research interest that I had in my university, and I'll briefly go through the work of 3 of my PhD students who have by now graduated and moved on. So how do we define integrity? Integrity is defined as using tool techniques or any kind of approach to ensure that the system behaves correctly. And that effectively means that if the input is correct and as expected, the system will generate desired output. The input might be constrained. We may have some privacy constraints. We may have some PII masking that is in place to hide or obfuscate personal information. But all that matters is that we look at the output and we check whether that's the desired output or not. If, however, we are concerned with how we establish security, what we are doing is we check that our system is robust. And robust means the system doesn't fail, doesn't fall apart if we're dealing with an attacker, and that attacker supplies unexpected input. So it has to be both correct and robust. And so what was I looking at are a number of things. What are the issues when we are building high-integrity software intensive solutions? I brought Alipay and WeChat, and I'm trying to be as not controversial as possible, because I recently went to China, and what is my surprise when here in the cafe next door, they didn't take cards. In China, it's exactly the opposite. They don't take cash. Whatever you do, you cannot pay in cash in any establishment. So what is the issue with having all your data controlled by an app? What is the issue of using WeChat, which is a very popular app in China, which people use to communicate excessively? It is based on WhatsApp. It has the same functionality, but of course, if you ask a local resident, they will always deny that. What is the issue of you communicating exclusively with WeChat and paying exclusively with Alipay, which is the payment platform? The issue is that you're identifiable, and the issue is that also in a country where a lot of transactions are monitored, your transactions are monitored. Whatever anyone tells you, unfortunately, it won't be the case. So looking at how we can ensure that if a transaction is monitored, the user is happy with that monitoring is something that we could think about, especially if we move on to another world where we all pay by card and all our transactions are recorded. How do we also model that? How do we ensure that our intention was correct, our transactions were correct, they were completed within the expected time, they were costing the same amount of money, they were recorded correctly, the records were private? All of these issues I have been concerned with. Security, I looked at security protocols, in particular message exchange protocols. I will be brief here and will tell very briefly of how we can model exchange of messages in one of the software platform, which is the model analyzer Alloy, my favorite analyzer because it uses the typed first-order logic. I was also concerned with data knowledge and process management, and that means ensuring that the data is secure, ensuring that the knowledge reaches the right person at the right time. Meaning in disambiguation, can we preserve, kind of transformation of the data? Can we still preserve the meaning? This may sound somewhat superfluous, but it isn't necessarily true. Sometimes when you manipulate a relatively simple data, strip it of a certain characters, you get a completely different meaning. And also, I will talk a little bit about how I transmit data and what tools and techniques have I used for that. And these are my favorite tools, and I'll tell you why they're my favorite tools and what I have done to improve them. Alloy, my favorite tool because it uses type first-order logic. I've worked with first-order logic, so it's a match made in heaven. Spin, a model checker, which I have extended by allowing it to include time in the transaction, exactly for the reason that I just mentioned. In a man-in-the-middle attack, I wanted to be sure that the attack happens at the expected time, and if it happens at a different time, it's actually not man-in-the-middle, because the man can be only in the middle if he intercepts your message at the right time. Uto, another framework, which I use to model transmission again of messages and data exchange. And all of these three tools I have used to work with three of my former PhD students, by now graduated. So what is the issue with using such tools? I didn't hear anyone mentioning that, and I'm curious, but I didn't want to ask and interrupt this already lengthy meeting. How are people concerned with modeling dynamic exchange, and how are people concerned with modeling some situation which doesn't really proceed as expected, but instead something happens, something disrupts the dynamic? And so that is what I have been looking at. Can we use our code to establish and formalize security constraints? Can we define the security policies as code? And how do we approach that challenge of looking at the static versus the dynamic setup and scenario? How are we doing security testing, vulnerability scanning, and policy management? This was another topic of interest. In Alloy specifically, what can we do? So I don't know how familiar you are with Alloy. I had planned to give a demo, but this will delay me further, and I'm aiming to finish in half an hour. So you can go and look at Alloy and download it at MIT's website, and it will have a very much similar to Emacs interface. What is it based on? It's based on modeling any system as a state and a state transition, and operations between transitions of the system is what we want to capture. This is actually what is happening also when you want to capture any kind of information exchange, and when you want to prove that the sender is who they say they are, or the receiver is who it is intended to be. If you have a static model, the situation is a lot simpler. So what you have is just a set. A set is a collection of components without repetition, and a predetermined, predefined set of relations. How you will define it would depend on your problem domain. So what do we want? We want for any kind of reasoning or any kind of tool that we are using to prove some properties, we want to be able to specify the constraints in the language of the tool. For Alloy, that would be typed first-order logic, and what we want here to be able to express is how many times we expect a certain action to happen, what is a fact in our model, what is a realism constraint, what can we realistically expect to happen, what is representative of our world as we know it. Dynamic models are more interesting, which will allow us to express the sequence of actions So when we look at the static representation of the world, we are describing this as it is, as we understand it. But if I look at dynamic state of the world or dynamic idea of the world that they have, then I will need to be able to express how the transition from state to state happen. And this is one example. So if I want to check whether the right sender sent the message and the right recipient received the message, then my realism constraint would be, I must have sent the message before it was received. It seems trivial, but with all of these tools, which I have been working with, there is no built-in notion of semantics, there is no built-in notion of understanding. That is why I was very curious about what Ian mentioned, the notion of ontology. Ontologies are those structural formalisms which could give you a constraint on what happens before what, in terms of ISA or HASA, which are the two paradigms that the ontologists allow to support. And here is an example of a message model in a line. So we have a person, and both the sender and the recipients are people, and then you want to say that they're a subset of person because that is what you would expect. And you probably want to check whether someone who claims to have sent the messages they themselves, similarly for the recipient, you will need to formulate a lot more properties in logic so that you can do that. But here what you have is essentially just this property for this particular example, that you have only one signatory. And that might be important because then you can check whether your signatory is the one that you expected. And in your model, which will be generated by the tool, you can specify more properties and you will see the relationships expressed quite clearly depending on how your signatures and your predicates look like. So if you have this way or this task to model a state transition, then you will need to find a way around your static model. How would you do it? One way is to introduce a time signature. I have been very curious about what we can do with the time signature, and that's why I have introduced explicitly in a lot of models modeling message exchange in Alloy, but also in SPIC, because the signature of time naturally has this ordering constraint. So you add a component to each relation, and that component changes over time where the relation stays the same. This is important for some properties which necessarily describe security properties and which happen all the time. The issue here is that signatures are static, and there is another example. When we again revisit our model of a person who sends a message at a given time, so notice here we have a mapping from the set of people to the time, and the recipient receives the message at a certain time, and we have one signatory. And then we may want to be concerned and find some statistics of what type of users are sending the message, or what type of attacks happen to whom. This is something that we deal with also at Microsoft when we are looking at how the data is targeted. We're looking at when the data is compromised by whom, what is most likely to happen based on the time. So this is just a very simplistic way to express properties that might be of interest. The issue here is that signatures are static. You have no way of using this signature to trace what is happening over time. That is the bad news. The good news is that you can actually find a way around, and you may want to think about expanding your static models with thinking about how they evolve over time. And you can do that by introducing a mapping and tracing how the components of your system or how the components of whatever you're describing will vary over time. So here in Alloy, we also have this notion of multiplicity constraints. If you're not familiar with the language, it doesn't matter for the moment. The only thing that matters is you're looking at set. There is no restriction on the number of components there. And we are looking at how many people there are, how many senders, how many receivers at a given time. So lone here means one or less than one. And what do we want to do? If we want to add more relations, we may want to define them separately, and we may want to say that at a given time we consider those people who we have identified as possible senders. But how do we add that? And that is how we would do that. For the property that you want to express, you will identify it as a label. Here I have just used a trivial example where I say that whatever the attack, I'm thinking about how living people will have their communication compromised. This is an example. It doesn't have to be alive. You could also look at those bots that are attacking your system, and in this case could be dead. But what you will have is a separate component here in your signature where you will specify a property, and that property will hold over a certain period of time. And so if you think about it, you may expand these static constraints that you would have normally and make them all dynamic. And here again, for easier understanding, I have given some trivial examples which relate to a family dynamic because that is what could be easily understandable. So when you're looking at how the message is transferred through the network, it goes from a sender to a receiver, but it might be followed through a trace. And that is one way to express that someone cannot be their own ancestor. So you can say you can use those transitive closures or reflexive transitive closure to express that if you look at a successive message exchange, it doesn't happen that this message that you have just sent has not been sent, for example. And you could have a lot more constraints which are related to how many senders, how many messages, how many recipients, all of these are static. If you want to make them dynamic, you will introduce that additional mapping going to time, and you will need to modify every static property that you have originally defined and introduce the timestamp so that your static constraints are no longer static, so that you have a way to trace how the time label changes with time. Example here again to add to that. So you may have, for example, transition from a time t to time t prime. And what you will need to do is you will need to expand your predefined relations so that they can model and express that dependency on time. And when you do that, in your models, you effectively have a sequence diagram. So here is an example of who was born when, but you can think of someone sending a message, and this message is transmitted from someone to someone, and effectively what you're doing with this kind of state sequence formalization is you're expressing at any point in your system what is known by whom. So how do we express a transition in a law? In a law, as a type first order logic, everything is a predicate. A predicate is another relation. And if we're thinking about any kind of transition that you would want to have, you're looking at what happened right before the transition and what happened right after the transition. So in order for us to be able to express that, we need two variables, one for right before and one right after the transition. And then if you want to have realism constraints or properties that will realistically express what is happening, then your predicates will also have t and t prime to express what happened over time. You will also formalize this in using precondition, postcondition, and frame condition. You may be familiar with the 4 triples, which essentially state that what you have as a postcondition is consistent with what you formulate as a precondition. It is exactly the same when you try to express the transition in a law. So you formalize what needs to be true before the transition will apply. What will be the effect of the transition? when you go to the next page. And the frame condition is what remains static. And what remains static means what doesn't change. So there will be always properties in your system when you're exchanging information that the sender will send something, the recipient will receive something, but you want, for example, the message content to never change. And that is what you would want to model. And if you do that, if you describe all these pre, post, and frame conditions in a correct way,
It's working, right?
Part of the time, people mention SDK, and that's also something they want to ask questions all the time, but I also refrain myself, so I get a further bonus point. The reason why I bring this up is when we say SDK, we actually don't know what SDK means. There is no clear definition of what SDK is. But what we know for certain, whether we are talking about SDK or not, is that documentation is critical. For a lot of these security problems, for a lot of the formalizations, we need documentation. For SDK, we also need documentation. My team worked on providing SDK for exactly this data platform that I just mentioned in the beginning of my talk. So if you have the correct pre, post, and frame conditions in your exchange of information, what you have is useful documentation. I'll not talk to you about this example, but essentially, if you are married or even if you're single, stay single, but in any way, you have an example of what properties hold at what time. And if you have an intuition about these properties, then you can separate them, you can identify what is precondition, what is post-condition, what is frame condition, and then you can use the law to make sure that it makes sense. And so the frame condition is very important because for a lot of security properties, you would want certain things not to change. You would want the data not to change, that is the property of data integrity. You would also want the password perhaps not to change, or the timestamp of the time when the message was sent not to change, and that would be a frame condition. If you have a frame condition, you have a documentation, and the documentation will give you useful guidance when you have this formal model. So not talk about this. I will talk about instances. If you have a message exchange and you have formalized it to have a sender, a recipient, and the time, then effectively what you have is what in a law is called an instance. And an instance is a snapshot of how the world looks like. Since it is typed first order logic, what we have effectively is typed variables and the way to access this notion of transition. Very important for security properties. So for every trace, the trace is a way to follow what is happening in the system. So for every trace, that is what would hold. You have the time and you have the first step in your time period, and this step must satisfy some initialization condition. And then if you have a secondary step, then all the consecutive steps will be related by an operation. And so you can do that and you can formalize it. If you're thinking about message exchange here, you can state anything that you want to be true, to be factual, and you can specifically specify what holds as a fact at a certain moment in time. And then you can check using Alloy how you can build a model of that and whether that is consistent. That is also useful when you're modeling quite a few security properties, and sometimes you will find out that it is not possible to satisfy them all unless your model is large enough. Realism constraints, again here, if you're running a specification in Alloy, You need to know how many states are of interest to you and how many phrases are of interest to you. And once you do that, your reason constraint will specify for how many of them you run in the model. That is essentially what we did in Alloy, using man-in-the-middle attack as an example. And then we recreated that in Spin with the addition of time, just that was consistent. Own what man-in-the-middle is, I will not remind you, we have experience man-in-the-middle as well. So we're interacting in messages or dropping connection, that's fine. Things don't change. And if we modify the data, then the data will change. This looks like in a naive diagram. And for us to be able to specify these properties, we will write what the properties that will be, and we'll have to assert that something is true, and then look at the specific model size and check whether indeed that is true. So this is one of our runs. The way Alloy works is it decomposes those paired first order logic formula into small instances, and then it tries to do a verifiability reasoning, tries to break them down to propositional bits which are either true or false, and combine them in a way so that the model is satisfied, depending on what conjectures there are here. If Alloy gives you an output like this, no counterexample found, assertions may be valid, that is informative of course, but it's not definitive. It very much depends on your model size. That is something that one will need to experiment. Model training. Now, do I have time? How much time do I have?
Yeah, 15 minutes.
Okay, okay. So model checking. This was now, up to now was model analyzing. And now we're going to do exactly the same thing with a different tool, model checking. There are different communities, all clustered around different tools. And what I was wondering about is how useful those tools are. So what is model checking? You probably all know as well. We have some finite state model of a system, and we have some logical property, and we really want to check whether this property holds for a given state in that system. So we have an abstraction of the system, we have a certain set of properties which interest us, and we are trying to find out what is going on over time. So here for my work, over time was critical because if we abstract from time and we are looking at the static snapshot of the world, then we're even further removed from what is actually happening in the real world. What is the nice thing about model checking? Just like everyone, we have an automatic checking process, and it is really fast, faster than what you saw in the previous slide, which was still in milliseconds for a smaller model. And again, you can use first order logic, this time even better without types. So you can express many properties that you can directly reason about in Spin. If you use temporal logic, it will be the linear temporal logic, which is simplicity in context of the branch and temporal logic. It's again philosophical debate. Do you want to trace the execution of a property of a system over the state of the system as it changes? What can we do with model checkers? You can verify protocols, you can verify software, and you can also use some interactive interface for Spin and have an interactive simulator where you can vary some of your properties in real time and see what is going to happen. The syntax here, arguably, to me, this is simpler, but it depends on which programming language you're most comfortable with. You have a type, you have a channel, you have some time, and these are defined depending on your needs. The language is called Prono. It has fairly strict syntax rules, which are, however, comprehensive. What did we model? We looked at one example of online banking application where we first have to authenticate and then we have to do session management and look at whether we will succeed for executing a simple payment, simple transaction, or not, depending on what properties we have. What else you can do? You can model web applications. Again, we were very interested in web applications which need to be secure, and they were all related to payment systems. And we modeled here whether the input values are consistent with what you would expect, whether the output is consistent. You can think of it as transferring money or not. In terms of modeling authentication, that happened at the very beginning, because at the very beginning, just as you, when you're interacting with your online banking or with your ATM, you have to identify yourself. And at the beginning of the session, you have to enter your credentials and they need to be correct. And then, in order for you to perform that session, that transaction successfully, you need to, of course, maintain your internet connection, which we saw was a challenge here, and that means that you have to not be locked out. What is called session needs to be maintained through the communication. There are a lot of challenges. I think that they are no longer that strict, but a few years ago, there were timeouts when one was interacting with their online banking, and that was strictly set to 2 minutes. I haven't seen that strictly even with my own bank. Maybe things have changed since I last investigated that. But in order for us at the time to model session management, we had to use non-deterministic timeouts, which are given during the session. So you can imagine someone using an online service of some sort, just forgetting about it. And that means that the session will need to be abandoned, that it cannot proceed, and the transactions will be cancelled. And we modeled request to login, request to log out, and forced log out. Here's one simple example of what was involved in that modeling. And this is a visualization of the simulation of the model and the various states, which maintain certain values very similar to a loan. The person who is interacting with the account remains the same. Time changes, but the request by that person, that agent, user, call it any way you want, the request also stays the same. And as a result of this request, their balance is updated or not, depending on whether they have the credential in the money or not. We did some similar exercises to simulate that over time, and time here was critical. And that was DT spin. DT spin was extension of spin with time. UPO, my last tool of the day. Another tool to define graphical models and to verify them. Less intuitive than a line, and purely graphical. Depending on your preferences, it will give you the option to check some properties as well. So in UPO, everything was focusing on the design, whereas in Promova, it was focusing on expressing the properties in this language of the tool. But we compared what kind of processes you can express in one tool versus in another, and what you can do in Spin. And we are satisfied that UPO and Spin were fairly comparable, in contrast to Alloy, which allowed for more expressivity, but on a larger model. Oh, and that's surprisingly my last slide. I must have deleted the thank you slide, so thank you for your attention. So the work here was on looking at what kind of security properties we can express with these three different logic formalisms and how do they compare. So thank you. Absolutely.
So any questions from citizens?
Apparently not.
I have a small question.
Sir, go
You
ahead.
had this model where the girl was born,
Oh, yes.
and I saw that it was sort of already existing in a certain no previously. First one, yeah, this one.
Okay.
So when you list the persons there,
Yeah.
and while in the life expression is still empty, it's already there as a person. Is that just an artifact, or is it something to watch out for? Does it classify different types of artifacts?
Yeah, that's an excellent question. So when you're modeling your system, you may find out that just modeling the sender or the receiver is not enough. You need something extra. You need them to be active, for example, in that time. So when you add a live, it's a different predicate, it's a different property that highlights that if that person is active at that particular moment, only then they will interact with your system. Here, the intuition is that you can only get married if you're alive, basically, or if you're married. You cannot get married if you're dead. I mean, that sounds macabre, but you can think of no one can send you a message online if they're not connected to the web. So this gives you a different information with a different predicate. And you can have more of these. The issue is that when you add more formalization to your problem, the diagram that the lawyer will generate for you will become more complex, and then it's harder to understand. But it's useful because it's more information.
Thanks.
So one quick question from the objectives perspective, a quick one.
Go ahead.
So are there any plans to carry on what are the new challenges from EPL perspective? Or if you prefer, we can discuss again the report.
This is a very good question. In an ideal world, if I quit my industry job, I will have another PhD student looking at how we can make these models realistic and unambiguous, because the big challenge for any system of the above mentioned is that one can formalize the same property in a different way and get a different intuition. And that's fine, but for those of us who are very excited by ChatGPT, not me, you see that there is a whole new field which we are now being sold as field of computer science, which is called prompt engineering. Prompt engineering is a bogus thing. I'm not on record, I hope. And it's a bogus thing because with ChatGPT, which is based on different formalism, if you do prompt engineering, you're not guaranteed to get the same answers from your prompt. With Alloy, if you do the corresponding to prompt engineering formalization of the system, you will get the same answer, so that's good. So the constraints you need would be very interesting.